Okay, wonderful. Thank you very much, Martin and Milena, for the invitation also to present today. It's really I'm really inspired to be here, and I'm really honored to be here actually, especially since similar, I think, maybe to Teresa, who also made me feel better actually about also not being a mathematician. I like to consider myself a math enthusiast in a way, and hopefully the work here is interesting for those of you who have some interest also in the connection between material behavior and mathematical concepts. So yeah, so I'll talk a little bit about some physical work and some digital work that resulted from a sponsored graduate research studio that I led recently, last semester in the spring of 2021. We were lucky enough to be semi remote and semi in person, and we had our fabrication machines available to us. So I led this project with 12 graduate students of architecture, where we tried to explore and kind of scale the geometric principles of various types of surface disclinations, as defined specifically by William F. Harris, who was a crystallographer in the 1970s, who kind of made a connection between what he was observing in crystals to surfaces. And the work proposes a variety of physical and computational form finding techniques that demonstrate the principles in architectural workflow. So just a quick introduction to Harris's disclinations as they were described by him. So the basic concept of disclination acknowledges the role of the defect in the composition of a twisted or warped material. So here the wedge disclination, which is a specific type that I'll refer to often throughout the presentation, they're created here by inserting or removing a 60-degree wedge of bubbles to alter the rotational symmetry of bubble lattices to either 5 or 7-fold. So of course, circle packing will have hexagonal arrangement. By inserting by either removing or inserting a 60-degree kind of raft of bubbles into the matrix, you end up with something here that on the left you can see has some some positive curvature, and on the right negative. But what's interesting, I think, about the disclination specifically is how the defect, quote unquote, or the position where the bubbles were added or removed cannot be identified. The concept itself can be applied to a larger scale in different kinds of material systems. So maybe some of you are familiar with the work of Alison Martin and her recent collaboration with a few architects. And they also explore the process of strategically inserting geometric disclinations in woven lattices. And this produces really wonderful out-of-plane buckling that produces concentrations of either positive or negative curvature. So there's something really wonderful about building these models and just sort of watching them automatically take form. And interestingly to note here, the defect in this case is clearly visible in the center. Now, studied at a much smaller scale, and a lot of this work, I think the terminology especially comes from this, but in crystallography, so for instance here, the interesting work, I think, of Taronas and McKay and Ijima, Ichihashi, and Ando. Since carbon atoms are already arranged into a hexagonal lattice, it is possible to build complex molecular structures with curvature by strategically inserting disclinations. So on the left, we see controlled shape change in graphite. Now in architecture, we see similar hexagonal framework consisting of several wedge disclinations occurring as well-placed pentagons, which of course allow for a spherical form of the structure. So it's also interesting to note here, Japanese chemist Osawa, who predicted the existence of the soccer ball shaped molecule that we now know as the Buckminster fullerene, by observing actually how scientists were making use of the same geometric rule set used subconsciously by traditional basket weavers. And here you can kind of note on the right where you would insert a kind of a heptagon or a pentagon into a hexagonal lattice in order to produce the closed vessel. But what I think is really interesting about Harris's contributions were that the connection to thin surfaces and how they buckle by absorbing the strain. So I think it's a really great manifestation of the relationship between geometry and topology, which is something that I'll kind of briefly discuss again when we get to the Gaussianbeneath theorem. But this also works because thin sheets absorb the strain induced by disclinations by buckling into these repeatable complex forms. So for example, in flexible sheets, this results in surfaces that they also do not reveal their defect that forces the curvature through self-reaction, which I think is really elegant as a formal response. And whilst the physical behavior is similar to that of woven lattices, I think this particular characteristic is unique. So you can see that the pattern is continuous across the surface, regardless of the physical action that's required to create it. So taking this a little bit further, the wedge disclination here illustrated kind of like a top-down view, if you can imagine it. It's basically a saddle-like surface. And this is created by just inserting, if you can imagine inserting one disk into another by first making a cut in the disk from the radius out, from the center point out. So if you insert so in this case, the wedge that's inserted is another full circle. And again, the seams where the edges are joined could be completely hidden, and any grid or pattern drawn along the surface could be continuous. This is an important characteristic for fabrication that I can touch upon a bit later. And just really quickly, just in terms of kind of understanding how they work in lattices and kind of cubic lattices, this is another illustration by Harris that shows that. So again, a bit of a removal and a bit of an insertion will create either positive or negative curvature. And a couple of different types also exist. Just kind of quickly, you may have seen, and I wanted to acknowledge this, you may have seen similar objects that appear out in the world, and especially in sculpture, especially here with Nam Galbo spheric theme. This is a manifestation of Harris's surface disclination that I showed earlier. And of course, the developable work by Ilhan Koman. I really love these. Their naming also is really quite nice because of instead of relying on measuring angle deflection and such, he simply refers to the number of circles needed to make the forms, or more accurately, how much pi is used in order to create these surface deformations. And perhaps this work is often used to teach mathematical concepts such as phase defects and angle deflections that myself, I'm also still learning about as I create and make things. And then similar surface bending occurs, of course, with the concentric curve crease folding techniques, illustrated both in the early 20s or the late 20s by Albert's design course at the Bauhaus and later on, and then more recently with Eric and Martin Demaine's work. And then just, I wanted to also acknowledge the Vera Hall and Vera Hall work on the Lovepreet sculptures, which actually, very interestingly, we also sort of discovered a very similar technique for creating the digital models of these surfaces, kind of without really quite knowing about this in advance. But I found his work very clear and actually quite helpful as we moved into digital form making. So a little bit about the Gaussianbeneath Theorem and how it kind of, I guess, relates. Now, I think it's very possible that Gaussianbeneath could help mathematically describe the surface disclination for us. It seems as though it's absolutely related, but the process to demonstrate the sculpture is slightly different. So here I'm actually taking some work from a friend and colleague, Edmund Harris, who has a very clear explanation, and I'll just use it here. He explains that the sum of the angles in a triangle is 180, and by changing the corner angles of the triangle will then bend. It must bend with either positive or negative curvature. So in other words, we shift from Euclidean polygon to both elliptic and hyperbolic surfaces simply created by changing the corner angle. So if we just rotate the corner angle, the material itself will react and it will bend accordingly. And the technique by DeltaThurston pushes the curvature to the seam. So it's a very similar idea, but instead of concentrating the curvature in the vertices, we see it here in the edges. So considering again the equilateral triangle, a 30-degree sector of a circle replaces each edge. And when the curved seams are forced to connect, bending is forced into the surface. Very interestingly, the meandering profiles are added to kind of get a much more smoother bending profile in the form. So as you kind of interlock the seams, the surface will automatically come together and the curvature is formed. Okay, so a little bit about how this kind of works. Here's a paper model version of our own here. So this is, here we can see two circles connected to form a spiral, and the rotating of the edges away from one another to reconnect the two ends of the spiral result in this kind of saddle-like surface that we described earlier. So the result here is the same as kind of inserting an entire disk into the gap of the other. But where things get really interesting, I think, is where we kind of start to observe this kind of snap-through buckling that exists between the two stable states. So this object will have two stable states that kind of just, that they'll rest in. But if you can kind of rotate them through You can sort of see the little white piece of tape that was once on the inner part of this the surface is now on the outer, facing the outer part, right? So through this kind of snap through buckling, we have a sort of inversion of what it could be considered inside and outside of the surface. This tension between the two stable states for us has been really interesting to think about how that could be used structurally. Just another example, where using squares instead of circles. And so in this phase of the research, we've developed a simple methodology, which was just to explore the surface disclination topology based on 3 simple geometric shapes. One being the ellipse, or the circle as we saw earlier, the square as we're seeing here, and then the triangle, which I'll show next. And there's a couple different techniques. One is just kind of a rotation away from itself, and then other is another way of doing it where you can bend it against itself. The rotational part for the takes a little bit of practice, actually. The other way to do it is a bit easier. So the triangle-based disclinations are really quite interesting because they tend to rest in a state that is visually less appealing. They sort of look twisted in the beginning, as you can see in this demonstration. But by forcing the twist to even out, we arrive at a tense middle ground between the two states once again. And we started to test how the two modules can oppose one another to create a more stable structure, which we should see here. All right, hopefully the videos are coming through smooth, not too choppy. But here we can kind of see how two opposing disclination modules can be connected to kind of oppose one another and form a self-stabilizing, I should say, structure. So in a sense, it's kind of a reverse tug of war. So each module is sort of holding back the other, using the potential energy that's inherent to the material itself. And this requires materials that will resist bending, such as thin plywood or metal to a certain extent. So our work in bringing disclinations to a larger scale, fabrication, appears actually similar to the DeltaThurston work, but I have to admit that our seams aren't quite as clever. The seams here don't force the curvature in the same way. Actually, the topology does. But the seams in this case are serrated because we're using a 2-layer construction in order to scale up. It's one way to avoid the limitations of standard sheet stock material, so 4x8 here in the States, 4 foot by 8 foot. But the seams between the layers avoid one another. So they're kind of staggered against one another so that there's always a continuous 2 layers of material across any given seam, which means that the surface will bend as though it is continuous and whole. This is just a couple of cut sheets showing also the importance of grain orientation relative to where they'll bend in the structure, which we see here. So this is one of our larger scale prototypes that we produced last semester. You can see that we used a kind of a sewing detail for this. They were all sewn together by hand, which through CNC drilled holes. And the sewing technique was quite effective in keeping the 2 layers of wood together without any air gaps in between. So the bending was actually quite natural, even though we exceeded the limitations of a single piece. There's a few others that we built as well. This is a 3 ellipse negative degree wedge disclination prototype. And here we used carbon fiber rovings that were kind of stood off from the surface in order to provide some added stability. And then finally, we built a third prototype, which is in this case a 6-module, 18-square negative X wedge disclination prototype. And on the left, there's just a kind of a 2-square carbon fiber kind of reinforcement test. I should say that the large ellipse that we saw earlier, that one is stable to a degree, but the carbon fiber played a huge role in keeping it sort of, much more stable. This one, on the other hand, is actually quite robust. It has a large footprint. And it also, of course, has much more curvature, so you'll end up with a stronger surface. But what's interesting, I think, about the square disclination and the triangle, really, but the square as well, is that because it has flat or kind of like straight edges, if you will, they tile quite easily. So I guess on the one hand, we were studying how we can harness this kind of like tug of war bending. On the other, we were studying how we might actually add, another system to stabilize it. And in the third, we were looking at how the disclination tile to form larger structures. And this is just an example of that. Here, again, the square and triangle have interesting potential to tile in multiple directions. While we were working, and I don't have a lot of good imagery for this just yet, we're still documenting some of the paper models experiments, of which we built hundreds. But we did find a lot of surfaces to be reminiscent of approximations of Shirk towers, which you can imagine pretty simply here. I think gyroids, Schwartz P, batwing minimal surfaces, as well as maybe Schoen's FRD surface, which again, I think I didn't want to show too much of that because I can't make a direct claim, but I do think there must be some relationship between, how these surfaces are being formed, how they tile, and potentially their ability to approximate known minimal surfaces. And so for me, this is a very exciting area of further investigation to both, mathematically connect surface disclinations to Gauss-Bonnet, and then vice versa, but also to find a way to control their creation so that we can arrive at specific periodic surfaces that are known to exist. I think I have a little bit of time to maybe just a few minutes, 4 minutes or so, to just maybe talk a little bit about how we've been using digital modeling to simulate some of this stuff. So computationally, we're exploring physics-based bending simulations using triangle mesh models. I can speak more specifically about each technique, but really one of them was to kind of look to expand the expansion of concentric polylines and have that as a counterforce against the bending to produce, the buckling, which has been effective, but a bit brute force. And maybe even more brute force than that is kind of just increasing the surface area of the circle and allowing it to just simply relax into its stable form. So this is just dynamic relaxation using bending, and it just kind of pops into position sort of naturally. And I have a video of that later. But maybe more importantly, we've developed some simple techniques for geometrically constructing the surface disclinations for accurate simulation work. So using just simple strings of conic sections. We found that it's very simple actually to build out at least an approximation of the surface disclination just using cones. Here, two double cones are intersected with a sphere on the left, which produces a curve in space that looks a bit like the seam of a baseball. And from there, a mesh is created with bending forces applied. And then there's some variations on that theme on the right here, just using cylinders instead to intersect instead of the sphere to create a kind of a tilted double ellipse, if you will. And then the square disclinations, we used a similar but different technique, different arrangement of cones, and finding the intersections actually just through the tangential connection between the cones themselves, and looking for different ways to approximate that base topology, which we could then simulate further using the physics-based algorithms. So just another, I guess, just another image of a similar process taking place here. But this is slightly different, actually, I should say. I mean, here we have a set of cones, well, different than the first image that I showed. This is one that I think we've started to adopt more prevalent, a little bit more in our work. And maybe just walking through the animation of it would be helpful. This is sort of just a screen capture of the digital modeling playing out. So this is the first example where we're just basically expanding the concentric mesh edges and forcing that to interact with the bending forces of the mesh. And then you have to straighten it out just a bit in order to make it developable. And then there's just a test on that to make sure that the mesh is truly developable in the way that we expect it to be. And we found it to be extremely accurate. Very small percentage of deviation. And then in another version of it, we can sort of just add surface area by folding it up and then relaxing it out and letting it just sort of pop into place. It's quite similar in effect to the way that the paper models feel, but this is of course not how they're created. But we didn't find it necessary to fully reproduce the physical making into space, because it's really an approximation for digital analysis further on down the line. And then finally, just another example of that. Here again, demonstrating the kind of conic and the cone sphere intersection and how that creates the initial seams or the edges, I suppose. And then this is actually a pretty trivial step afterwards, which is just to simply create the mesh and allow it to sort of, again, relax into its form. So it's sort of a combination of the two that we just saw. because it relaxes first, and then we can expand the mesh edges that are concentric in order to produce more or less curvature, thereby approximating, adding more or less pi, if you will, to the original circle. And of course, it unrolls similarly. On the right, it's just a diagram, which is the next step, which is to take then the unroll of this, the unrolled surface, and then break it down into discrete pieces from which we could start to fabricate our parts. And we found it really interesting that, you know, even though, and I'll just sort of end on this kind of, I thought it'd be fun for you guys to see the students in action, but there's a note about here, I think that's important, which is that we were a little concerned actually that because the paper model is a whole and you bend it against itself so easily when it's at a small scale by hand, that, you know, that same bending might not occur when we build it kind of piecewise. But we found that not to be true. Actually, the topology really takes over, and we had no reason to wet the material. We didn't have to use steam. We really were just able to sort of bend them into place. And if we had the sequence right, we found that the topology did the rest, and the surfaces were able to kind of just self-react and hold themselves into the exact forms that we expected. And that brings me to 21 minutes. So I think I'll end here and just sort of, yeah, and just let this play out just a little longer. Thank you very much.